Good morning. My name is Davide Ferraro and I'm an application engineer at MathWorks. I work with academic institutions in Italy. I've been with MathWorks for 4 years in a variety of roles, including customer training and technical support. In this presentation, I will show you how you can integrate low-cost hardware platforms such as Arduino, BeagleBoard, and Riga Mindstorms NXT in your class for experimentation through project-based learning methodologies. Project-based learning is based on direct experimentation on authentic problems. The interaction with a real environment stimulates the student learning process and offers opportunities to explore and discover a complex problem with their own pace. Complex challenges allow students to apply what they learn in class, stimulating creativity and discovery. Working on a project may also offer opportunities to develop teamwork and an understanding of how an engineering application is conceived, designed, and developed. In this presentation, we will focus on the hardware-based approach of project-based learning. MathWorks products support many different hardware platforms that are suitable for teaching with the project-based learning methodology. If you would like to analyze all the available options, please go to the Hardware for Project-Based Learning page in the Academia section of mathworks.com. On the main page of mathworks.com, we can click on Academia. Then in the Teaching section, we can find Hardware for Project-Based Learning. And this page is including all the hardware that is currently supported for teaching with a project-based learning methodology. Today, we will focus on 3 specific low-cost platforms: Arduino, Riga Mindstorms NXT, and BeagleBoard. These popular and flexible platforms allow you to introduce different teaching methodologies through simulation and application deployment. From 2012 A release of MATLAB and Simulink and MATLAB and Simulink student version, there is built-in functionality to enable enhanced interaction and application building for Riga, Arduino, and BeagleBoard. Let me show how you can access these new features with an example using Riga Mindstorms NXT. We will then discuss more specific examples and application in teaching. The first step you have to do is to run the command target installer that allows you to configure your MATLAB installation. Let's type target installer. This command will start an installation tool that will allow you to access the features we're going to introduce today. The installer will connect to a repository and identify all the available hardware that you can connect to Simulink. You can select the specific hardware that you want to install and then click Next to start the installation. This interface will install the required libraries as well as additional help, a set of demos and tutorials, and all the drivers and compilers you need to work with the hardware from Simulink. In example, you will get some additional documentation. Inside Simulink documentation, target hardware. You also get access to a set of specific demos for the hardware. Demos for Arduino, Riga Mindstorms NXT, and BeagleBoard. We will start now from a specific Riga Mindstorms NXT demo called Roving Explorer. This is an example of a Simulink model developed to control the tribot Riga Mindstorms NXT robot. We are now seeing the model with the new Simulink editor, available from release R2012B. Please remember that the features we are going to see today are available from release R2012A and included also in MATLAB and Simulink student version. In this model, we can read sensor inputs through a series of blocks that are included in the library Target for use with Riga Mindstorms NXT that we have installed with the command target installer. These blocks are reading the input from encoders, touch sensor, sound sensor, light sensor, and ultrasonic sensor. This information is then processed through a block diagram in Simulink inside this controller block. The output from the controller is then sent back to the robot using some actuators block like motors, speaker, and LCD. As soon as the model is ready, I want to run it on the target hardware, our Riga Mindstorm NXT robot. I can connect the robot to my PC using the USB cable. We may then run this model with two different configurations, an automatic and a manual approach. Let's start with the automatic approach. We execute the robot in an embedded configuration, removing all the communication with Simulink. All we need to do is go in Tools, Run on Target Hardware, and then click Run. After clicking on the Run button, the deployment process starts. As soon as the download is completed, we can remove the USB cable and the robot is now programmed with a basic control algorithm for obstacle avoidance. As you can now see, the robot is now running independently from the PC. A second option is to use external mode, allowing a Bluetooth communication between the PC and the robot. This mode allows the robot to exchange information with the PC during simulation. To enable external mode, we can set the switch to manual, we can check that the simulation mode is set to external, and then we can go to Tools, Run on Target Hardware, Options. In the option, we can flag Enable External Mode and press OK. At this point, we can just, as we did before, click on Tools, Run on Target Hardware, and then Run to start the deployment process of the model on the robot. As soon as this process is completed, we can remove the cable. The communication is now offered by the Bluetooth connection. We are now ready to exchange some parameters in the model and see what happens on the robot. In example, I can open and close the robot close. So let's change a parameter in the constant block, and the close opens, and then close. Or I can change the speed and move the robot forward and eventually have it turn around. Let's now step back on our three low-cost hardware platforms. We will see the typical application of these devices and the opportunities available for applying project-based learning methodology. Arduino can be a perfect choice to test your algorithms with hardware. You are able to develop communication between a PC and the board, or to design your application on the PC and then deploy it on the board for standalone execution. The board is a perfect solution for teaching algorithms, test and measurement, and control application. Riga Mindstorms NXT is a popular choice for developing simple robotic systems. Thanks to the rich set of sensors and actuators, this hardware can be customized for many different applications. The design phase of an industrial robot can be applied in an educational context, offering the opportunity to experience system design and software development using the same techniques available in the industry. The last hardware we will discuss is BeagleBoard. This low-cost open-source Linux PC has multiple input-output connections suitable for signal and video processing application. Depending on the specific class you are teaching, you may consider which of these platforms can provide you the best hands-on experience for the students. To provide you guidance on this choice, we will review possible application with Arduino, Riga Mindstorms NXT, and BeagleBoard. The first platform we are going to introduce is Arduino. Arduino is an open-source microcontroller board. Due to the popularity, many different versions have been developed to increase the board functionalities. Additionally, there are a variety of add-on products called shields. Each shield offers a specific set of additional functionality. The price of the board is only $40, making this hardware easily accessible for teaching and research. The Arduino is well suited for analog and digital input-output as well as motor control application. The board has an associated C-based development environment that allows you to develop algorithms to be compiled and deployed to the board. To facilitate project-based learning, we want the student to focus on the challenge while minimizing the time spent on writing and debugging code. The approach we are going to see offers us the opportunity to use MATLAB as well as Simulink for an immediate application design on the board. If you want to use the board in a project, you need to connect it to sensor and actuators. Depending on the nature of your class, you may have different options. If you would like to have your students practice on electrical networks, you may like to use an external breadboard or a breadboard shield. This approach allows the student to design the electrical system first and then control input and output from MATLAB. If your shield do not require any specific library or instruction, it can be easily interfaced with MATLAB and Simulink. All you need to do is to map the relation between the Arduino pins and the board ones. If you would like to avoid to introduce electrical networks and your focus is on the algorithm design, you may consider to use a specific shield such as Tinkerkit. The special shield comes with a set of ready-to-use sensors such as potentiometers and buttons, and actuators such as LEDs and mini servos that can be directly connected to custom pins. You do not need to build an electrical network. You can directly connect your components and start developing your MATLAB control algorithm. Arduino is a very versatile platform. If you're looking for opportunities to test your algorithms on a real board or design mechatronics systems, you may surely find in Arduino an optimal solution. MATLAB enables the student to experience the interaction with the board from a basic input-output approach to the actual system design for an embedded processor. Due to the large popularity of this board, you may find many different applications on the internet that you may quickly introduce in your class. Depending on the complexity that you want to introduce in your project, you may consider different approaches. A first interaction with the board can be achieved with the MATLAB support for Arduino package. Arduino is directly connected with your PC and an input-output communication is achieved through a serial connection. With this approach, you can easily acquire information from sensors, process in MATLAB using your own algorithms, and then send your output back to the board to control some actuators. Thanks to this tethered approach, you may have your students practice on basic algorithms or more advanced applications, in example control, test and measurement, signal processing, everything in connection with real hardware. The next step is to move from the algorithm to the realization of an embedded application to be deployed on the board. We want to program Arduino to execute specific tasks without being connected to a PC. The board becomes an independent system that can be installed into real-world applications such as robots, cars, airplanes control units. This is what we call embedded approach and can be implemented through Simulink support for Arduino. The system can be modeled and simulated in Simulink environment through block diagrams. The model is then converted into an executable to be deployed on the board. We will see how this workflow allows the students to experience an engineering design process focusing only on the design tasks without low-level hardware issues. Let's focus on the tethered approach first. As we have just introduced, the tethered approach is based on a direct communication between the Arduino and MATLAB. The USB cable connected to the PC allows us to transmit data back and forth with the board using serial communication. Through basic algorithms, you are then able to read and write information with an input-output approach. To start using this functionality in MATLAB, you may download the MATLAB support package for Arduino that is available on the Hardware Support for Project-Based Learning page we have seen before. This package contains a server application to deploy on the board that will take care of handling the communication with MATLAB and a list of simple commands to be used to control the communication. The abstraction of computer science is then transferred into an interaction with a real platform. Let's now see two simple applications of MATLAB support package for Arduino. This example is called Arduino Blink Challenge and is a simple programming task with Arduino. First of all, let's have a look at the hardware. We have an Arduino Uno board with on top a Tinkercad shield. The Tinkercad shield offers a series of input ports as well as output ports. Connected to the input port, we have a linear potentiometer. As an additional input connected to an output port, we have a button. The output port can be interpreted as a digital input port. All the other outputs are actually LEDs of different colors. Our challenge is to control the way that the LEDs blink by using the button and the potentiometer. We consider 4 different modes. In the first mode, all the LEDs should be off. In the second mode, all the LEDs should be on. In the third mode, all the LEDs should blink simultaneously with variable frequency regulated by the potentiometer. In the fourth mode, the LEDs should blink sequentially, like a wave, with variable speed regulated again by the potentiometer. The button should allow us to move from one mode to the other. Using the tethered approach, we can use a MATLAB script to acquire the input from the button and the potentiometer and control the state of the LEDs. Let's have a look at the code. With the command Arduino, we are able to establish the communication from the PC to the board. In the next section, we are initializing our pins. We are choosing if a pin on the board should be interpreted as an input or an output. The next section is the main algorithm section. This is based on an external while loop that's acting like a timer. Inside the loop, we are reading our inputs. We are reading the input from the potentiometer as well as the input from the button, and we are choosing the state of the LED using some if-else statements. We can then run the code and see what happens on the board. So let me click on Run. We are now establishing our communication with the board. So the PC is attempting the connection, opening the serial port, and as soon as the communication is ready, we can start playing with the board. So we can now click, in example, on the button to move from the initial state. Right now all the LEDs are off, so this is the initial state. With one click we should go with all the LEDs are now on. Another click, we move to the next state. In the next state, all the LEDs blink together simultaneously, and with the linear potentiometer we can make this lower or faster. Another click, we move to the last state. All the blinks LED sequentially like a wave, slower or faster. Again, if we click another time, we go back to the initial state. All the LEDs will go off. Let me now show you another possible and funny application involving Arduino and the creation of a MATLAB graphical user interface. I've now connected my Arduino board with the Tinkercad shield to a linear potentiometer, a rotary potentiometer, and the LED as an output. I've then created a graphic user interface writing about 100 lines of code. This graphic user interface includes some advanced concepts like timer objects and nested functions. My goal is to create a simplified version of a game like Arkanoid, Breakout or Pong. As you will see, the rotary potentiometer will control the ball speed, while the linear potentiometer will control the bar position. Let's start our simulation. As we have seen before, we are now opening our connection from the PC to the board. As soon as the connection is completed, is created, we can open the actual graphic user interface. Clicking on the Start button, I can start playing and use my linear potentiometer to control the bar. I can then use the rotary potentiometer to control the ball speed, making it slower or faster. I can then close my simulation and my interface. What's particularly interesting is that we are able to develop a simple and fun application communicating with an hardware platform in a short time, without the complexity of interfacing the PC with the external hardware. The application I've just introduced were based on a direct communication between Arduino and MATLAB. We refer to this configuration as tethered approach. If you would like to increase the complexity and realize an application written on Arduino that can run independently from MATLAB, you may move to the embedded approach. Run on target hardware, the new feature we have previously introduced in our example, enables you to develop a model of your algorithm in Simulink and deploy it to the Arduino board. You can then remove the connection and power the board with an external source. The board will now process input and outputs as described in your model without any connection with an external PC. This approach allows you to easily realize an embedded application through the same process used in the industry. Let's have a look at an example. The Simulink model is implementing the Blink challenge that we have previously seen with the MATLAB code approach. If you are not familiar with Simulink, Simulink is a graphical modeling tool that allows you to simulate, design, and implement dynamic systems. Simulink allows us to create our custom subsystem for inputs, for data processing, and for outputs. You may notice these spatial blocks. These are the blocks that house the communication with the board, and are taken from the target for use with Arduino hardware library that we have previously installed using the target installer command. We may have different approaches to solve our problem. It's up to the student to play with the model and identify an appropriate and efficient solution. In this case, you may notice the use of conditional subsystem like triggered or enabled subsystem that are controlled by the use of the button. As we have seen earlier, as soon as we have defined the interfaces and the algorithm, we are able to deploy it on our board. I click on Tools, Run on Target Hardware, and then Run. The model will be analyzed and an executable is automatically generated. The graphical diagram is then automatically converted into an application that is deployed to the board. The process is now complete. We may remove the USB cable. In this case, we will leave the cable connected to power our board, but you can remove the cable and connect an external power source. We may then test our board, so state 1, the initial state, all the LEDs are off. If I click, all the LEDs goes on. Another click and all the LEDs blink simultaneously with variable frequency regulated by the potentiometer. Last click, all the LEDs blink like a wave with variable speed, again regulated by the potentiometer. If I click again, all the LEDs goes off. Let me summarize the benefits of using MATLAB and Simulink with Arduino. We have two different approaches, tethered and embedded, that allows you to control the project complexity as well as the goals. If your project is focused on programming, surely MATLAB and this language can be an appropriate choice. As soon as your goal is to model a more complex system, you may consider moving to Simulink and to the application deployment approach offered by the Run on Target Hardware feature. Both MATLAB and Simulink offer a suite of algorithms and blocks developed for specific application that allows the student to focus on the system design rather than on specific algorithms or functionalities. Let's move to our second hardware platforms introduced today, Riga Mindstorms NXT. LEGO produces a complete solution for the development of simple robots. A LEGO Mindstorms NXT set usually contains a control brick based on an ARM processor, some servo motors, a set of different sensors, and many construction elements that allows the student to creatively build new robots. These platforms has a really high flexibility being based on the LEGO construction system, allowing you to develop a project targeted for various applications. So, why you may consider using LEGO in your class? In a project-based environment, the student can experiment a full design cycle from the initial design to the testing. LEGO allows the students to build a robot on his own. As soon as the design is complete, the robot logic can be designed and tested through experiments on the hardware. Depending on your goals and students' experience, you may consider different approaches to this hardware. You may start from a simple interaction with the robot suitable for high school students, or develop a full development process for a mechatronics course at university level. In the first example, we have seen the process that allows us to deploy a Simulink model on the LEGO robot. What we want to do now is to establish a workflow based on simulation, design, and implementation as adopted in the industry. We will call this workflow Model-Based Design. To develop an embedded system, we may need a full process that allows us to simulate the robot and design the controller. Model-based design is the detailed process used in industry that goes from the research phase to the implementation through different phases including simulation, code generation, verification and validation. For teaching purposes, here you can see a reduced version of this process suitable for application developed with run-on-target hardware. We start from model. We simplify our complex system into a mathematical form that allows us to analyze the system numerically. The equation can be translated into a Simulink block diagram for simulation. In this environment, we are able to predict the behavior of our system without testing on the hardware. In Simulink, you can design new components for the system, such as a controller. As soon as you have completed the simulation phase, you may be interested in moving your algorithm to the hardware. An application is automatically generated in Simulink and then deployed on the hardware. You can then test the behavior on the actual hardware. Let's see this design process on a simple control task for the Tribot robot. This is a simplified model of the robot to simulate linear motion. In the simulation subsystem, you can see the modeling of the motors that have been constructed through a data acquisition process with the real hardware. You may also consider to build more advanced models starting from the real physical configuration of the motor. To allow the robot to reach a certain distance, I've added a feedback loop with a PD controller. The controller design can be performed in many ways. In my case, I've used the Simulink control design feature called auto-tuning. By clicking the Tune button, the controller will be automatically tuned and designed. I can then modify the response time, or using the extended mode, I'm able to set a specific bandwidth and a specific phase margin. As soon as I'm OK with the design, I can click OK. And I have all the information I need to move this model to the actual hardware. In this model, the main block has been substituted by the encoder and motor blocks taken from the LEGO Mindstorm NXT hardware library that we have previously installed. The loop is now a control loop running directly on the actual robot processor, and this allows the robot to reach the desired position. I will now simulate with external mode, clicking on Tools, Run on Target Hardware, and then Run. Since the current position will differ from the desired one, the controller will generate a request to the motors and the robot will start moving to the goal. As soon as the download is completed, I can remove the USB cable. We are now communicating using Bluetooth connection, and I can change the desired position from 0 to 0.3, it's in meters, so 30 centimeters, and the robot moves 30 centimeters, and I can move the robot back, so setting back to 0. With this approach, you may start the development of more complex tasks and configurations. Let me summarize the benefits of using MATLAB and Simulink with Riga Mindstorms NXT. The LEGO kit offers you the opportunity to develop a robotic system from the concept to the actual implementation. By using Simulink, you can introduce in your project a real design flow that's typical in industry. The run-on-target hardware feature enables us to simplify the deployment process, making it possible to program the LEGO brick directly from Simulink models. The additional block set and tools allows you to simplify the design of algorithms and controllers for specific tasks. The last hardware I will introduce today is BeagleBoard. BeagleBoard is a low-cost open-source board with laptop-like performances with a TI ARM Cortex-A8 processor. The board offers a large set of connections, including USB and video plugs. Thanks to this high number of possible connections, it is commonly used for signal and video processing applications. So, why you may consider using BeagleBoard in your class? As we have just introduced, this board enables the student to easily practice with signal and video processing applications. As an example, a standard webcam can be directly connected to the board that will acquire the data, perform image processing algorithms, and then output the processed signal back to an external monitor. This goal can be achieved through executable applications in the same way as discussed for Arduino and Riga Mindstorms NXT. Let me show you an example. Let's analyze the problem configuration. Our BeagleBoard is connected to a PC through Ethernet. This connection allows us to deploy the code and eventually control the execution through external mode. As we have seen with the LEGO robots, the external mode allows us to have a communication between the PC and the hardware during the simulation. This communication can be used to tune parameters or to log the data. The BeagleBoard is then connected to a webcam to acquire images and to a monitor. If we do not have an external monitor, we can send the image back to our PC using the external mode. We are going to introduce a simple object detection algorithm. Our goal is to identify one or more red objects in the image. The BeagleBoard acquires an image from the webcam. The image is then processed through a series of image processing blocks. These blocks are part of the computer vision block set, a tool specifically developed for video processing application. Essentially, the algorithm will extract the red chroma component of the image. A blob analysis is then performed to identify the shape of the image, and the rectangle is created around this image. We are able to tune a filter depending on the light conditions. As we did before, the deployment of this model on the board is very simple. We just need to go on Tools, Run on Target Hardware, and then click Run. This will start the deployment process of the model to the board. As soon as the deployment process is over, we are now communicating using external mode with the board. In this way, we are able to get back on our screen the image processed from the board. As you can see, we are identifying some red objects, like this one, or the small icon on top of the box. The other objects, like this pen, are not identified. We can also see the actual board, so I can show you the connections. We have a power plug connected to power up our board. We have an Ethernet connection. This is enabled our external mode. If we use an embedded approach, we can then remove the connection. And we have our webcam, the one that's recording this image. The algorithm is identify a red object dynamically with the video, so I can move this cap. And as soon as the image is part of my screen, the red object will be identified. Let me summarize again the benefits of using Simulink with BeagleBoard. As discussed with previous hardware platforms, the one-click executable generation approach allows your students to interact with the hardware, avoiding working with low-level functions and interfaces. Simulink is also offering a wide set of functionalities for image and video processing application that makes it easy to develop advanced algorithms typical of the industrial work. Please remember that the run-on-target hardware feature for Arduino, Riga Mindstorms NXT and BeagleBoard is available from R 2012A onwards. This feature is currently Windows only. If you want to learn more about the features that you have seen today, please refer to the hardware support for ProjectBased Learning page on mathworks.com. This concludes today's presentation on MATLAB and Simulink support in teaching mechatronics application with low-cost hardware.